Hello and welcome to MKTG 685 Machine Learning in Marketing. In today's Colab session, we build a practical text classification workflow for marketing analytics. One key idea before we start: sentiment and emotion are related, but they are not the same. Sentiment is polarity, positive versus negative. Emotion is category, such as joy, anger, sadness, or fear. In practice, that difference matters because the same negative sentiment can imply very different actions depending on the emotion behind it. We will run two tasks in the notebook. First, binary sentiment classification. Second, multi-class emotion classification. We will start with a fast lexicon baseline to set intuition, then move to a supervised model using TF-IDF features and logistic regression. Along the way, we will evaluate with metrics that match the decision setting, and we will interpret results using the confusion matrix and a few concrete errors. Let's begin from the top and set up the environment and the data. In this first code cell, we set up the notebook for reproducible results and install the packages we will use today. Notice the seed value. It controls randomness in sampling and model training. So if you rerun the notebook, you should see the same splits and very similar metrics. Then we install a few key libraries. The Hugging Face datasets library for loading text data, evaluation utilities, and a couple of sentiment tools like VADER and TextBlob. If Colab already has them cached, this will run quickly. If not, it may take a minute, but this step prevents version mismatch issues later. In this cell, we import standard Python tools plus NumPy and Pandas for data handling and TQDM for progress bars. The important part here is that we set a global seed across libraries. This is one of the simplest ways to make your results stable enough for debugging and for reporting. At the end, the cell prints the fixed seed and the library versions. When you are collaborating or when you revisit a notebook later, those version prints are very helpful for diagnosing why a result changed. This cell creates a clean output structure for the notebook. We define a single output directory, then separate folders for figures, tables, models, and logs. That organization is practical because we will generate multiple artifacts later, and we want them saved automatically in predictable locations. Next, there is a quick TQDM sanity check. You should see a visible progress bar. This matters because later steps like dataset processing or inference can take time, and the progress bar helps you verify the notebook is actually moving. Finally, we define two small helper functions to save JSON and CSV safely, creating folders if needed. You will not notice the value immediately, but later it prevents silent failures when writing outputs. Now we transition into the data section. From here, the notebook runs two related classification tracks in parallel. The first track is binary sentiment, predicting negative versus positive. The second track is multi-class emotion, predicting a specific emotion label. We start with sentiment because it is simpler and it helps us establish correct habits for splitting, training, and evaluation. Then we reuse the same workflow for emotion, where the output space is larger and the confusion patterns become more informative. Now we begin the first data track, binary sentiment classification, using the Yelp Polarity dataset. We will build a balanced sample with the same number of negative and positive reviews. Instead of downloading the full corpus, we use streaming sampling, which keeps the workflow fast and Colab friendly. The labels are simple. Label 0 is negative and label 1 is positive. The main objective of the next code cell is to create a clean, reproducible dataset that we can reuse for both lexicon baselines and supervised models. In this cell, we define the sampling configuration and the streaming sampler. The key parameters are the number of samples per class and the shuffle buffer size. The buffer controls how well the streaming shuffle mixes the data. A larger buffer gives better mixing, but it uses more memory. Next, we define a small normalization function to clean up white space and make text consistent. Then we stream through the dataset and collect examples until we reach the target count for each class, and you should see a progress bar updating as we sample. At the end, we shuffle the sampled rows again using the fixed seed, so the final data frame is reproducible. Once the sampler finishes, we print the shape and the class counts. The important check is that the dataset is balanced, meaning the counts for label 0 and label 1 match. Now we do quick sanity checks to understand what the model will see. We compute simple length features, number of characters and number of words. Then we print summary statistics. Here is the interpretation you should focus on. Yelp reviews are often long and the distribution is typically right skewed. That means most reviews are moderate length, but a few are very long. This matters because long reviews often contain mixed sentiment, and that is a common source of classification error. Next, we print a few random examples from each class. As you read them, notice that real reviews are not always purely positive or purely negative. Many contain contrast words like but or however, which is exactly why we later need structured error analysis. In this cell, we create leakage-safe splits. We first split the data set into train and a temporary set, then split the temporary set into validation and test. We also use stratification so the label distribution stays balanced in every split. The key idea is that we keep the test split untouched until final reporting. Validation is for iterative choices like thresholds or model settings. Test is for one-time evaluation that you treat as your final report. After printing the split sizes and the label distributions, we save the sample dataset and all 3 split files as CSV. Saving these files is important because it lets you rerun later sections without resampling, which keeps your comparisons consistent across reruns. Now we move from binary sentiment to multi-class emotion classification using a standard 6-class emotion dataset. The key shift is that the target is no longer positive versus negative. It is a set of categories like joy, anger, sadness, fear, love, and surprise. Because this is multi-class, evaluation also changes. Accuracy alone can be misleading, so we will later emphasize macro F1 and a multi-class confusion matrix to understand which emotions are confused with which. For speed and consistency, we will build a small stratified sample for train, validation, and test, similar in spirit to what we did for Yelp. In this cell, we load the emotion dataset from Hugging Face. The dataset name is DARE/emotion. We set target sample sizes for train, validation, and test to keep training fast and Colab friendly. After loading, we print the label names directly from the dataset metadata. This is important because it prevents label mismatches. We also print the available splits and the number of rows in each split. When you see the output, quickly confirm 2 things. First, the label list contains the expected 6 classes, and second, the dataset splits are present and non-empty. Now we convert each split into a pandas data frame with a consistent schema. We standardize the text using the same normalization function as before, so downstream features are comparable, and we reduce noise from formatting issues. We keep the numeric label, and we also create a human-readable label name column by mapping label IDs to the label list. This is very helpful later for interpretation, especially for confusion matrices and error analysis. At the end of the cell, we print the full data frame shapes for train, validation, and test. This is a quick sanity check that the conversion worked as expected. In this cell, we create stratified samples for train, validation, and test. Stratified sampling means we take roughly equal numbers from each emotion class, so the model sees a balanced training signal and our metrics are not dominated by one frequent class. You should see a progress bar as the sampler iterates through the emotion classes. That progress bar is useful here because sampling can still take a moment and you want visual confirmation that the process is moving. After sampling, we print the sampled shapes Then we print label counts by label name for each split. The key interpretation is simple. The count should be close to evenly distributed across the 6 emotions. If one class is much smaller, that can affect macro F1 later, so this check is worth doing every time. In this cell, we print a couple of example texts for each emotion label. This is a quick but important sanity check. If the examples do not look like the label, the rest of the pipeline becomes meaningless. As you read these examples, notice something crucial. Emotion labels are often more subjective than sentiment labels. Some texts can plausibly fit more than one class, depending on interpretation. That label ambiguity is one reason we will later rely on macro F1 and the confusion matrix, not just accuracy. Now we save the emotion dataset splits to disk, train, validation, and test, plus one combined sample file and a small JSON config. This step matters for 2 reasons. First, it makes the notebook reproducible. Second, it keeps our comparisons fair because every model later will be evaluated on the exact same data. When you see the printed file paths, that is your confirmation that the dataset artifacts are now fixed and ready for modeling. This section is a reminder of the most important idea in this lecture. If the label changes, everything changes. The model choice, the metric you report, and the way you interpret errors. Sentiment is a polarity question, positive versus negative. Emotion is a category question, which specific effect is expressed. So even if both tasks look like text classification, they behave differently in evaluation and in error patterns. Keep that in mind as we move into baselines. Before training any supervised model, we build a lexicon-based baseline. The value is speed and transparency. You get a sentiment score immediately, and you can explain the output as a rule-based scoring system. This is especially useful for quick monitoring, trend tracking, and alerting. But you should treat it as a baseline, not a final answer. Lexicon methods struggle with domain-specific language, mixed sentiment in longer reviews, and context effects like negation or sarcasm. So our goal is to use this baseline to set expectations, then move to supervised models where we can measure improvement rigorously. Now we start a fast baseline with VADER, a lexicon-based sentiment tool. VADER outputs 4 values: positive, neutral, negative, and a single summary score called compound, which ranges from -1 to +1. In practice, we often convert the compound score into labels using simple thresholds. Scores above +0.05 are treated as positive, below -0.05 as negative, and values in between as neutral. This is not a trained model, but it is a useful baseline because it is immediate and easy to interpret. In this cell, we instantiate the VADER analyzer and score a small set of example sentences. Please focus on the compound column, as it will later be used as a single sentiment score. When you look at the output table, notice 2 important patterns. First, clearly positive sentences move toward +1. Clearly negative sentences move toward -1. And vague or balanced sentences stay near 0. Second, mixed statements like "great product but customer service was awful" often land in the middle. That is a key limitation of lexicon baselines. They can understate mixed sentiment, which is very common in real reviews. Finally, we apply the simple threshold rule to convert compound into a label. This makes VADER feel like a classifier, but the threshold is a choice, not a learned parameter. This cell shows the threshold rule on a small grid of compound values. Pay attention to what happens near -0.05 and +0.05. A tiny change in the score can flip the label from neutral to negative or from neutral to positive. This is why threshold selection matters in business settings. If you want fewer false alarms, you usually tighten the threshold. If you want to catch more negatives early, you loosen it. The model is giving you a score, and you control how aggressive the decision rule should be. Now we apply VADER to a real sample from the Yelp sentiment dataset. This step uses a progress bar while scoring because we are running VADER on many texts, not just a handful. After scoring, we convert the VADER rule output into a binary prediction so we can compare it to the true Yelp label. Notice what we do with neutral. For a binary comparison, neutral is treated as the negative class. That choice is practical for a quick baseline, but it is also one reason the performance can look weaker than you might expect. Then we compute accuracy and F1 based on the binary labels and ROC AUC using the compound score as a continuous signal. Here is the key interpretation. If AUC is meaningfully above 0.5, VADER is ranking positives above negatives better than chance. But if F1 is modest, it usually means the simple threshold rule is not well aligned with this dataset, or that mixed sentiment and domain wording are causing systematic mistakes. This is exactly why we move next to supervised models. The goal is not to eliminate lexicon methods, it is to establish a baseline and then measure cleanly how much we improve. Now we introduce a second lexicon-style baseline, TextBlob. It produces a single polarity score from -1 to +1, but it uses a different rule and lexicon system than VADER. The reason we include this is simple. Even when two tools output a polarity score, they can disagree on borderline or context-heavy text. That disagreement is a useful reminder that lexicon baselines are fast heuristics, not ground truth. In this cell, we define a small helper function that returns TextBlob polarity for a given sentence. Then we score the same demo sentences and sort them by polarity. When you look at the output, focus on the ranking. Clear positives should move upward, clear negatives downward, and mixed or vague sentences often land near 0. If you notice cases where the score feels off, that is exactly the point. Context and domain wording can break simple lexicon rules. Now we apply TextBlob to the Yelp sentiment sample and compare it to the true binary labels. You will see a progress bar while polarity scores are computed across many reviews. Next, we use a simple threshold rule to convert polarity into labels. We use +0.05 and -0.05, matching the VADER rule style, so the comparison is fair. Neutral is then mapped into a binary prediction for evaluation. Pay attention to what the metrics mean here. ROC-AUC uses the raw polarity scores, so it tells you how well TextBlob ranks positives above negatives, independent of the threshold. F1 and accuracy depend heavily on the threshold rule, so if they look weaker, it may be a threshold mismatch rather than a complete failure of the scoring signal. In this final cell, we save the TextBlob scored Yelp table and the metric JSON file. This is important because it locks the baseline outputs so we can compare VADER versus TextBlob and later compare both against supervised models using the exact same sample. Once you see the saved file paths printed, we are ready to move on to supervised learning, where the model learns domain-specific cues instead of relying on a fixed lexicon. Now we will do a short hands-on exercise to build intuition for VADER scores. You will write 10 sentences of your own, mixing clearly positive, clearly negative, and neutral or mixed statements. Then we will compute VADER compound scores and visualize the distribution as a histogram. The goal is not to optimize anything here. The goal is to see what kinds of language produce extreme scores, what lands near 0, and how your sentence mix changes the overall shape of the score distribution. This intuition will help you interpret baseline outputs later, especially when a model looks confident but the text itself is mixed. If you are following along, pause now, replace the placeholder sentences with your own 10 and then run the next cell. If needed, please pause here and then resume. In this code cell, we start with a list called student texts. These are 10 example sentences and you should replace them with your own. Next, we pass the list into VADER scores, which computes the VADER outputs for each sentence, including the compound score. Then we apply a simple rule-based label using the compound threshold function. This is the same idea we used earlier: positive above the positive threshold, negative below the negative threshold, and neutral in between. We displayed the table sorted by compound score. When you read the output, focus on the ranking. The sentences at the top should sound clearly positive, and the sentences at the bottom should sound clearly negative. If a sentence you expected to be negative appears near zero, it is usually because it contains hedging, mixed sentiment, or words that VADER does not treat as strongly negative. Finally, we plot a histogram of the compound scores. Here is how to interpret the shape. If you wrote mostly positive sentences, the histogram will shift to the right, with more mass above the positive threshold. If you wrote mostly negative sentences, it shifts to the left. If you included many neutral or mixed sentences, you will see a pile-up near zero. A balanced mix often looks roughly bimodal, with one cluster on the positive side and one on the negative side, plus some values near zero for mixed statements. The main takeaway is that lexicon baselines produce a continuous score, and your decision boundary is a separate choice. The histogram helps you see whether your text stream is mostly positive, mostly negative, or largely ambiguous. Now we move from lexicon scoring to a supervised baseline, TF-IDF features with logistic regression. This is a strong classical standard because it is fast, stable, and surprisingly competitive for many real marketing text tasks. The most important habit here is leakage safety. We fit the TF-IDF vectorizer only on the training split, and then transform validation and test using that same fitted vectorizer. If you fit TF-IDF on all data, even accidentally, your performance will look better than it should. In the next cells, we will train the model, generate probabilities, and evaluate with metrics that match threshold-based decision-making. In this cell, we train the TF-IDF plus logistic regression baseline using the Yelp train split, and we evaluate first on the validation split. Notice the TF-IDF settings. We use unigrams and bigrams so the model can capture short phrases like not good or would not recommend. We also limit rare terms with min document frequency and cap the vocabulary size for speed and stability. Then we fit logistic regression and generate predicted probabilities for the positive class. This is important. Probabilities let us choose decision thresholds later instead of treating the model as a fixed yes or no rule. When the metrics print, focus on two things. ROC AUC tells you how well the model ranks positive above negative across all thresholds. F1 at a threshold of 0.5 tells you how well a single default decision rule performs. If AUC looks solid but F1 is not great, that usually means the ranking signal is decent, but the threshold is not tuned to your business objective. Now we evaluate on the held out test split. This is the final report for this baseline. We do not tune anything based on test results. We treat this as a one-time estimate of real performance. Again, we compute ROC AUC using probabilities and F1 and accuracy using a 0.5 threshold. Here is the interpretation that matters. Compare validation versus test. If test performance is close to validation, the baseline is stable. If test drops a lot, you may be overfitting decisions on validation, or the sample may contain harder cases. In this cell, we save two artifacts, a test metrics JSON file and a prediction table that includes the original text, the predicted probability, and the predicted label at the 0.5 threshold. This prediction table is extremely useful. It becomes the input for the next section where we build the confusion matrix and do error analysis. Instead of guessing what the model is doing, we can inspect concrete false positives and false negatives and learn exactly which language patterns cause mistakes. Once these files are saved, we have a clean baseline that we can compare against any future model in a reproducible way. At this point, overall metrics like AUC and F1 are helpful, but they do not tell us how the model fails. For marketing use, that is a problem because different mistakes have different costs. So now we do two practical checks. First, the confusion matrix to summarize error types, false positives and false negatives. Second, representative misclassifications to see concrete failure patterns like negation, contrast words, and long reviews with mixed opinions. This is the step that usually gives the most actionable insight. In this cell, we compute the confusion matrix for the test set using the default threshold of 0.5. Read it like this. Rows are the true labels. Columns are the predicted labels. In the example output shown here, true negatives are 339 and true positives are 321, which are the correct decisions. The off-diagonal cells are the errors. There are 36 false positives, meaning the model predicted positive, but the true label was negative. There are 54 false negatives, meaning the model predicted negative, but the true label was positive. Here is the key business interpretation. False negatives are missed positives, for example, satisfied customers that the system fails to recognize. False positives are false alarms, for example, complaints incorrectly flagged as positive sentiment. Which one is worse depends on the use case, and that leads naturally to threshold tuning later. Now we build an error table from the test prediction table. We first tag whether each row is an error, then we label the error type as FP or FN. Next, we add simple pattern detectors. We flag negation words like not or never, contrast words like but or however, and we compute word count. Then we create a mixed sentiment proxy, which is basically long text plus contrast cues. The most important output here is the top wrong table. We rank errors by confidence wrong, meaning the model was very confident but still incorrect. These are the most informative cases to read because they reveal systematic failure modes, not random noise. When you skim those examples, you will usually see patterns like negation scope, mixed opinions in one review, or subtle context that a bag of words model struggles with. Now we save the top wrong examples to a CSV file so we can reuse them in discussion or in a report. Then we compute a quick pattern summary by error type. The important interpretation is directional, not perfection. If a large share of errors contain negation, contrast terms, or long text, that tells you what to improve next. For example, you might add more phrase features, use better sentence handling, or move to models that represent context more directly. The output of this section is not a single number. It is a clear explanation of what breaks the model and why. Now we will do student exercise 2 on decision thresholds. The classifier outputs a probability of positive sentiment, but your decision rule comes from a threshold. In this exercise, we will compare 3 thresholds, 0.3, 0.5, and 0.7. Your job is to connect the threshold choice to business cost. When is a false negative worse than a false positive, and when is it the opposite? Also notice an important detail we will see in the output. AUC is a ranking metric, so it does not change when we change the threshold. What changes is the confusion matrix and the decision metrics like accuracy and F1. In this code cell, we evaluate the same test probabilities at thresholds 0.3, 0.5, and 0.7. First, we compute accuracy and F1 for each threshold, and we report AUC as a constant reference. When you look at the results table, confirm that AUC stays the same across thresholds. That is expected because the probabilities themselves did not change, only the cutoff did. Next, we print the confusion matrix for each threshold. This is the most important part. At threshold 0.3, the model predicts positive much more often. You should see very few false negatives, but many false positives. This is a high recall operating point. Useful when missing positives is costly. At threshold 0.7, the model predicts positive much less often. You should see very few false positives, but many false negatives. This is a high precision operating point. Useful when false alarms are expensive. At threshold 0.5, you typically get a more balanced trade-off. The key takeaway is simple. Threshold selection is not model training. It is business decision design, and you should choose the operating point that matches the cost of mistakes in your specific application. Now we begin emotion classification, which is still text classification, but the task definition changes in an important way. In sentiment, we predicted one polarity label. Here, we predict one of multiple emotion categories, so the output is a distribution over classes. Because of that, evaluation also changes. We will focus on macro F1 per class performance and the multi-class confusion matrix. The most important mindset is that errors are not all the same. Confusing anger with sadness is a very different mistake from confusing joy with love, and those differences matter for marketing actions. We start with a fast classical baseline for multi-class emotion prediction, TF-IDF features with logistic regression. This is a useful baseline because it is fast, easy to run, and fairly interpretable, so it gives us a clear reference point. At the same time, it is limited because bag of words features miscontext, intensity, and subtle cues that often distinguish emotions. For reporting, we will use macro F1 as the main metric because it treats each emotion class equally. Then we will use the confusion matrix to see which emotions are systematically confused. In this code cell, we train a TF-IDF plus logistic regression model for 6-class emotion classification. First, we build TF-IDF features using unigrams and bigrams. Bigrams matter here because short phrases can change emotional meaning. Then we fit the vectorizer on the training split only and transform validation and test with the same fitted vectorizer. That is the leakage-safe workflow. Next, we train logistic regression and generate predictions for validation and test. We compute macro F1 and accuracy for each split. When you read the printed output, focus on macro F1 first. Accuracy can look higher than macro F1 if the model does well on easy or frequent classes, but struggles on harder ones. Macro F1 forces us to care about performance across all emotions. Also compare validation to test. If test is close to validation, the baseline is stable. If test drops a lot, the model is not generalizing as well as we want, or the sample contains harder cases. Now we create the multi-class confusion matrix on the test set. Read it row by row. Each row is the true emotion, and each column is the predicted emotion. The diagonal cells are correct predictions. Off-diagonal cells show specific confusions. Do not treat this as just an error count. Use it to identify patterns. For example, whether negative emotions get confused with each other or whether joy and love are frequently mixed. In this cell, we save the key artifacts for the emotion baseline. We save validation and test metrics as JSON, the test prediction table with predicted labels, and the confusion matrix as a CSV. Here is how to interpret a multi-class confusion matrix in a meaningful way. If the model often confuses anger with sadness, that typically happens because both emotions share negative language, complaints, and problem descriptions. The difference is often expressed through subtle cues like blame, intensity, punctuation, and context, which a bag of words model can miss. In marketing applications, these confusions matter. Anger may require escalation or service recovery, while sadness may reflect disappointment and expectation management. so the confusion pattern can map directly to different managerial responses. Now we extract the most common confusions by removing the diagonal and ranking the off-diagonal pairs. The output table shows which true emotion is most frequently predicted as which other emotion. This is a fast way to summarize what the model systematically mixes up. When you look at the top pairs, ask one question. Is this confusion understandable from language alone, or does it suggest the model is missing context that would require a stronger representation? Now we pull actual text examples for one confusion pair. For example, true anger predicted as sadness if that pair exists in the test set. This step is where interpretation becomes concrete. Read a few examples and look for the cue the model missed. Is it intensity, blame, threat language, sarcasm, or negation? Often the words are similar across emotions, and the distinction is in how the message is framed. The takeaway is not that the baseline is bad. The takeaway is that this baseline reveals exactly what bag of words can capture and what it cannot. That sets up the motivation for the next section, where we use a pre-trained transformer for stronger language understanding. Now we run a pre-trained transformer for emotion classification, inference only, with no fine-tuning. This is not a strict research comparison. It is a practical demo of a modern workflow. We load a pre-trained model, run inference to get predicted labels and confidence scores, and compare the behavior against our classical baseline. Two cautions matter here. First, pre-trained emotion models often use label sets that are similar but not identical to our dataset labels, so the comparison is not always perfectly apples to apples. Second, transformers typically handle context better, but they are less transparent and require more compute. This is a bridge to the next part of the course on transformer-based models. In this code cell, we load a Hugging Face transformer model for English emotion classification, and we create a text classification pipeline. Notice two details. We request all label scores, not just the top one. And we enable truncation because some texts can be long. We also choose GPU if it is available. Otherwise, the pipeline runs on CPU. Next, we run inference over the emotion test sample. You will see a progress bar, and that is important because transformer inference can take time, especially on CPU. For each text, the pipeline returns scores for multiple labels. We normalize the output shape first, because the pipeline output format can differ across versions. Then we select the top label by score, and we store two things, the predicted label name and the confidence score. At the end, we preview the first few rows of the table. The key columns to notice are the predicted label and its confidence score. High confidence predictions are easier to interpret. Low confidence predictions often indicate ambiguous text or overlap between emotion categories. Now we try to map the transformer's predicted label names into our dataset label space. This step is necessary because even if both are emotion models, the label inventories may not match exactly. We do a conservative mapping by normalizing label strings and keeping only direct matches. After mapping, we print how many inference rows we have and how many are directly mappable. The mapping rate is a key diagnostic. If it is low, you should treat this section as a qualitative demo, not a strict metric comparison. If the mapped subset is large enough, we compute macro F1 and accuracy on only that subset. When you read these numbers, interpret them carefully. These metrics reflect performance only on the mappable labels, not the full 6-class task, so they are informative as a sanity check, not a definitive benchmark. We save the transformer inference results and a small config file. Once the file paths print, section 6.2 is complete. Now we will do student exercise 3 using the transformer emotion model. Your task is to write a small set of your own sentences, run transformer inference, and then interpret both the predicted emotion and the confidence score. Focus on two things. First, do the predicted labels match your intuition? Second, when the model is uncertain, do the sentences feel genuinely ambiguous to a human reader? The goal is not to prove the model is perfect. The goal is to practice reading model outputs like an analyst, where confidence and error patterns matter as much as the top label. In this code cell, we start with a list of student sentences, replace them with your own examples, and include a mix of clearly emotional sentences and borderline cases. Next, we run the transformer pipeline on each sentence and capture all label scores. Then we select the top predicted emotion and its score. When the results table prints, read it row by row. If the predicted emotion matches your intent and the confidence score is high, that is a straightforward case. If the predicted emotion matches but confidence is low, that usually means the sentence contains overlapping cues that could fit multiple emotions. If the predicted emotion does not match your intent, check whether the sentence includes sarcasm, negation, or a shift in tone, because those often trigger misclassification. Finally, look at the full score distribution for one or two sentences. If the top two emotions have similar scores, that is a signal the text is borderline. In real marketing workflows, those borderline cases are the ones you would route for human review or treat cautiously in dashboards. Now we move from a single sentiment score to something more actionable, aspect-based sentiment. A single overall sentiment label is often too coarse for marketing decisions. Managers usually want to know what the sentiment is about, for example, price, service, quality, delivery, or food. True aspect-based sentiment can be complex, but here we build a lightweight MVP that still works in practice. The workflow is simple. We split each review into sentences, match each sentence to one or more aspects using keywords, score each sentence with VADER, then aggregate the results into an aspect-level report. The goal is not perfect linguistic accuracy. The goal is a table that behaves like a manager-facing dashboard input where you can prioritize what to fix first. In this code cell, we implement the rule-based MVP. First, we define an aspect dictionary where each aspect is represented by a small list of keywords. This is intentionally editable. If you are working in a different domain, you should replace these keywords with your product and service vocabulary. Next, we split reviews into sentences using a simple punctuation-based rule. Then we match aspects by checking whether any keyword appears in the sentence, case insensitive. One important detail, a single sentence can match multiple aspects, and when that happens, we record one row per aspect. For speed, we run this on a sampled subset of Yelp reviews, and you will see a progress bar while we parse sentences and score them. At the end, we build a sentence aspect table. Each row is one sentence, one aspect label, and the VADER compound score plus a tri-label, negative, neutral, or positive. When the output prints, look at the total number of sentence aspect rows. If it is very small, it means your keyword coverage is low and you should expand the aspect keywords. Also skim the first few rows to confirm the aspect assignments look reasonable. Now we aggregate the sentence level table into a manager-style aspect report. For each aspect, we compute the volume, which is the number of matched sentences, the average compound score, and the share of negative, neutral, and positive sentences. Then, we sort the table in a very practical way, by negative share first, and then by volume. This prioritizes aspects that are both frequently mentioned and disproportionately negative. Here is how to interpret the columns. High negative share indicates a likely complaint driver. High volume indicates the aspect is frequently discussed, so it has high business relevance. The average compound score is a quick summary of direction, but the shares tell you whether the aspect is consistently negative or mixed. Finally, we save both outputs, the sentence level table and the aggregated manager report, so you can reuse them in a dashboard or a write-up without rerunning the parsing step. Here is the manager style way to read this table. Start with aspects that have both high negative share and low average compound. These are your most likely complaint drivers. Then check volume. An aspect with high negativity but very low volume may be real, but it is not a top priority yet. For example, if service ranks highest in negative share, you would investigate service recovery, staffing, or support scripts. If price is frequently mentioned but mostly neutral, pricing is salient but may not be the main driver of dissatisfaction. If quality shows mixed sentiment, the customer experience may vary across customers, batches, or use cases, which suggests a consistency problem rather than a universally bad product. This MVP is intentionally simple. It is a starting point that creates actionable structure from raw text, and it also motivates why more advanced methods can add value later. Now we focus on robustness, in other words, what tends to break sentiment systems in the real world. Instead of theory, we will automatically collect misclassifications and tag them with common patterns, such as negation, mixed sentiment, very long reviews, sarcasm cues, emojis, and language shift. The goal is to produce a small, concrete set of cases that explains why errors happen and what kinds of fixes would actually help. In this cell, we build a full case table from the supervised sentiment test predictions. We start by flagging whether each row is an error, then we tag simple pattern features. You will see a progress bar while we compute text-based tags. These tags are lightweight heuristics, not perfect detectors, but they are useful for organizing failure modes quickly. At the end, we also compute a confidence score as the distance from 0.5, so we can identify cases where the model was very sure. When the output prints, quickly confirm the case table shape and that the new columns were added, especially the error flag and the confidence column. Now we extract the most informative failures, the high confidence errors. These are the cases where the model made a wrong prediction while being far from the 0.5 boundary, so they are the most surprising and often the most diagnostic. When the table displays, scan the pattern columns first, especially negation, contrast, and the mixed sentiment proxy. Then read one or two texts to see what the model is missing in those cases. Now we sample a few representative texts for each pattern bucket. For example, negation errors, mixed sentiment errors, emoji cases, sarcasm cue cases, non-English proxy cases, and very long reviews. The key is not the exact examples, it is the pattern. If you repeatedly see errors with negation or contrast, that points to scope and context issues. If very long reviews dominate, that suggests multi-opinion texts where bag of words models struggle. This is how you translate errors into next step modeling decisions. Finally, we save the high confidence error table and the full case table as CSV files. Now we wrap up by collecting the most reusable outputs from this notebook. We focus on 4 deliverables: sentiment baseline metrics, emotion baseline metrics, representative misclassifications, and the aspect-based manager report. These artifacts are what you will carry into later notebooks, so you can compare methods over time and build simple monitoring dashboards without rerunning everything. Thank you for watching the video. See you in the next topic.